Hello everyone, welcome to a new series. Today's topic is a very interesting topic and there is a lot of mysteries surrounding. We're trying to unfold some of these mysteries in this series. Today we are going to talk about fatigue of steel structures, and to make things even more interesting, we are going to talk about wind-induced fatigue. So let's get started. Here I'll walk you quickly through the contents of the series. We start with a little bit of introduction and then we move to the properties that qualify the load to cause fatigue damage. In the third section, we are going to lay out the different design limit states and how they are related to the fatigue design. Fourth section, where we get more detailed about fatigue design, starting with explaining the S-N curve and the key definitions that are widely used in the most of the reference books that talk about fatigue design. After that, we reach to the fatigue stresses section, which explains how to process stresses to be able to perform fatigue design, and then gives an overview of how the international codes like American Code, Australian, and Euro Code classifies the fatigue stresses and relate them to different modeling level. In the context of fatigue stresses, we have a separate section here that talks about specific type of stresses, which is the geometrical stresses, and how do we use finite element modeling to extract these stresses for the purpose of design. And then comes the section which handles the damage concept and how to use Miner's rule to plot the accumulative damage under variable amplitude cyclic loading. And then because of the importance of the American code, it is inevitable to use H2, especially to check fatigue for assigned support structure. The series provide an explanation of how H2 approach the fatigue design. Finally, there is a big market share of checking existing assets. That's why the last section here in this series will explain how fatigue is a governing factor in deciding the way we manage our important infrastructure assets. We're going to talk about introduction. So fatigue is a silent killer. The damage and the cracks happening due to fatigue propagate silently without us realizing that they are happening. If the damage happened in a critical location, it might causes a global instability for the whole structure. As we might have noticed, this science support structure looks like a brand new structure, but because fatigue happened in a critical location, it caused the whole structure to collapse. Collapse due to fatigue is sudden. It might be a global collapse or it might be partial collapse, as we see in the other three photos. What is fatigue? Fatigue is the initiation and propagation of cracks in a material due to cyclic loading over the structure's lifetime. There are 6 elements to that definition. First element is the material, second is the cyclic loading, and third is the structure's lifetime. The other 3 elements are related to the stages of fatigue failure. First stage is crack initiation, second stage is crack propagation, and third stage is obviously the failure due to fatigue. Okay, let's talk a little bit about the cyclic loading that causes the fatigue failure. We have 2 types of cyclic loading. We have constant amplitude cyclic loading and we have variable amplitude cyclic loading. We'll start with the constant amplitude cyclic loading. And to understand the nature of the cyclic loading, we're gonna give a real life examples. We have the horizontal axis for number of cycles and the vertical axis for the stresses applied to the loading. And top we have tension side and in the bottom we have compression side. For us to understand the nature of cyclic loading, we're gonna monitor and record the stresses at the orange dot shown here. Let's talk about first example, which bridge structure. The orange dot is under tension due to dead load, and once the truck passes by, it adds more tension. So the cyclic loading is varying completely in the tension zone between the dead and the dead and plus life. Then we're going to talk about turbine blade. In this particular position, the orange dot is under tension due to the self-weight of the blade. Once the blade starts to spin, the orange dot becomes in compression. So we can see that the variation of stresses is fluctuating between tension and compression. Then we're gonna talk about the inner service shaft, and we're gonna talk about the orange dot, which is under ring compression due to the hydrostatic pressure of the water filling the reservoir. The state of stresses is between full and empty, and the whole variation of stresses is within the compression zone. Okay, so what are the characteristics of the constant amplitude cyclic loading? First one is the mean stresses, which is the average between the maximum and minimum stresses. Second is the stress ratio, which is the ratio between the lower part of the curve to the upper part of the curve, the lower part of the curve to the upper part of the curve. Okay, and then the amplitude, which is the difference between the maximum and minimum stresses. And finally, the alternating stress, which is half of the amplitude. Okay, but life is not that simple. We're gonna talk about now the variable amplitude cyclic loading, which is a little bit complicated more than the constant amplitude cyclic loading. We have a noise wall here, which is basically a cantilever wall subjected to wind, and we're gonna monitor and plot the stresses on this orange dot. The wind induced stresses are variable. It doesn't have uh, fixed mean stresses. It doesn't have fixed alternating stresses. So we can see that the mean stresses changes from zero to tension to compression along the number of cycles which the wind load is happening over. The amplitude and the number of cycles for each amplitude is different from time to another. Okay, methods of fatigue assessment. The method of fatigue assessment is defined how much reliability do you have in the performance of the structures. There are four types of fatigue assessment. First one is safe life, and basically this is sort of build and forget. You build the structure, it's maintenance free, crack stays in the initiation phase, it doesn't propagate, and that maybe this method is as valid if your structure has no access for maintenance, for regular maintenance, or your structure is very important structure and consequences due to failure is pretty high. The second one is damage tolerant, and this damage tolerant, it allows for fatigue cracks to initiate and propagate, but the fatigue are readily detectable because you have a regular inspection, and that's enable you to detect the crack once it's happened. Once the crack happens, you either monitor the crack or repair the crack. Those two methods are adopted by the Australian code and the Euro code, and this is how those two methods affects the reliability, the performance reliability of the structure. For safe life, where there is no inspection at all, this is how the reliability and the performance decays with time until the design service life. And then with damage tolerant, we can see that there are times where you have to do your regular inspection, and obviously at the time where you do the regular inspection, you do some maintenance or some repair, and that causes the performance to boost. And this is how the reliability of the structure, reliability of the performance of structure changes with time, and these hikes happens at each time you do an inspection. The third method of assessment is infinite life, and it's used by American code, and this method just makes sure that the fatigue stresses are very, very low, so you do not expect failure due to fatigue. And this one is maintenance free, and it's suitable for structures that subjected to high number of cycles like chimneys. Fourth method is fail safe, and it depends on the fact that your structure is highly indeterminate and it's highly redundant, and the load path has a lot of alternative load path and it allows for fatigue failure to happen depending on the fact that there is a space for the redistribution of the stresses, and there is a time for replacing the failed member. Obviously, this method requires regular inspection. Two footnotes here. Methods of fatigue assessments define two things: define the life cycle of the structure and defines how much reliability you have in the performance of the structure. Based on that, you have your maintenance regime that dictates the intervals of inspections and the useful life of the structure and how you detect and repair the fatigue cracks. And then it defines also the strength reduction factor based on the reliability that you have in the performance of structure, which we use in the fatigue check.